Good day to you, sir. My name is Yan and I will be presenting the lab enhancements for Lab 4 K-means. These enhancements are designed to deepen our understanding of the lab material, applying it to the real-world datasets, and exploring more advanced concepts. Without further ado, let's start. Our first step was to pre-process our data. We loaded our dataset and performed several pre-processing steps, including encoding categorical variables such as gender, removing unnecessary columns, and scaling our features to prepare for clustering. This standardization is crucial as it puts all features on the same scale, allowing for meaningful comparison and analysis. Next, we tackled the challenge of determining the optimal number of clusters. We employed the elbow method, plotting the within cluster sum of squares, or WSS in short, against the number of clusters. As we can see in the plot, the WSS decreases as the number of clusters increases, but there's a point where the decrease plateaus, indicating the optimal cluster count. With the elbow method pointing to 5 as our optimal number of clusters, we applied the K-means algorithm with this parameter. K-means is a powerful clustering tool that partitions the data into distinct groups based on feature similarity. To visualize these clusters, we utilize principal component analysis, or PCA in short, to reduce the dimensionality of our data. This simplification allowed us to plot our data points and cluster centers in a two-dimensional space, making it easier to interpret our clustering results. Interpreting our clusters, we transformed the cluster centers back into the original feature space and calculated the silhouette score. This score helped us assess the consistency within clusters, and our results indicated well-defined clusters with a silhouette score that reflects good separation. We also explored advanced visualization techniques. By transforming the cluster centers, we were able to create a 3D PCA plot, providing us with a deeper understanding of the cluster distribution and separation in a three-dimensional feature space. Here's the 3D plot output, which visually demonstrates the distinct groups we've identified within our dataset. The spatial separation of clusters in this 3D plot further confirms the effectiveness of our chosen clustering approach. Finally, we leverage T-distributed stochastic neighboring embedding, or TSNE in short, which is particularly well suited for visualizing high-dimensional data. This technique allowed us to observe the data in a compressed form while maintaining the relative distances, thus ensuring that we can visualize complex structures hidden within our data.
Hello, my name is Student, so I'll be presenting this Lab 5 enhancement, which is the PCA right here. So in this enhancement, I have done some few models here. So the first one will be the feature engineering. So which the feature engineering you can generate new features when it captures the most important variation in the data. So after new features have been captured, and then they will be used as inputs to machine learning models so that they can improve the performance. So this is the code explanation here. You can look through it right here, and then this is the code for it. And then the next enhancement I have done noise reduction, which the PCA could help in reducing noise and extract signals from data. So in some scenarios, there are some data will be corrupted by the noise, so it contains redundant information. So by using PCA and noise reduction here, will clear out all the redundant information and those corrupted data. This is the code here and the description for it here. Then the third one will be the compression model, which the PCA can use it to represent original data, but it is in a smaller number of principal components. and also remaining all the important informations. And this is the code, and then the description is right above it. And the last one I'll be presenting will be the last enhancement, the method for image processing. So PCA could be used to do image processing such as denoising, feature extraction and compression. So by applying PCA to images, redundant information can be removed, leading to more efficient processing and storage. So you could see that image processing could be done when PCA is involved in the model. So you can look through it. This is the code, and then this is the image that we are seeing from the data. Okay, so that's all from me. Thank you.
Anyway, for the lab exercise, I choose to do lab 8 for logistic regression. So for the first enhancement is I do a real-world application for multinomial logistic regression using the one recognition dataset. So these are the codes. For second enhancement, I do how to apply hyperparameter tuning. So for the dataset I use is the adult.csv. So this is the part to pre-process the data. And for parameter, the first parameter is the type of solver. So we have 5 types of solver here, and the details are listed out here. So these are the code for the testing out for the accuracy and their training time. So it's printed out here, and here are the findings. So for the second parameter, it is the penalty. So only Saga solver can apply all these penalty. We have 4 types of penalty with non L1, L2, and elastic net. So this is the code how we are applying the penalty and compare them. So these are the result output in terms of training time and accuracy. So that's all for the lab exercise. Thank you.
Good day to you, sir. We are Group 15. My name is Chin Yuan Wai, and the issue we have chosen is the rental price in Kuala Lumpur, Malaysia. The reasoning behind this selection is that we have discovered that it is a norm of the rental price in Kuala Lumpur to be higher. Thus, we will be implementing clustering to identify the pattern of the rental prices in Kuala Lumpur, find the reasoning behind it, and also predicting the rental prices while utilizing linear regression. Firstly, we will take a look at the pre-processing part of the project. This stage is essential as it sets the groundwork for our entire analysis, focusing on a significant real-world problem in Malaysia. Let's begin by understanding how we've transformed our raw data into a clean, analyzable format to ensure accuracy in our findings and efficiency in our computational models. Our first challenge was handling missing values. As you can see, we cleaned and converted this feature to numeric values, replacing any missing entries with 0. Then we applied an interquartile range method to remove outliers. Next, we tackled categorical variables. The getDummies function was instrumental. It converted categorical variables like property type into a format understandable by our algorithms. Each category became a separate column with binary values. Here, we standardized our numerical features using standard scalar. This step is crucial because features like size and rooms differ in magnitude and can skew our model. We then move on to dimensionality reduction using PCA. By setting n components to a value that retains 95% of the variance, we reduce the number of features while preserving most of the information, streamlining our model without significant loss of data. To refine our feature selection, we use a correlation heat map. This visualization was key to identifying highly correlated features. For example, bathrooms was highly correlated with size, indicating that as house size increases, so does the number of bathrooms. To avoid redundancy, we decided not to include bathrooms in our final model. We made informed decisions based on the correlation heat map. For instance, bathroom was excluded because it's redundant with size and rooms. This not only simplifies our model, but also helps in preventing issues like multicollinearity, which can compromise our model's performance. Our pre-processing is now complete. We've handled missing data, transformed categorical variables, scaled features, and executed dimensionality reduction. With these steps, our dataset is clean, concise, and ready for the next stages of our analysis.
Hello, my name is Jensen. So in this assignment part, I have done the linear regression part here, which is summary here. Yep, this linear regression part, I have done this part. But for today's video, I'll be presenting the EDA part and the linear regression part. So let's start. So in this EDA, we have basically lots of data will be shown in histogram graph like this. So if you can look through it here, and there's a description below all the graph. So in this histograph, you can see that the mean of this distribution for multi-rand of KL Selangor region is around 1462 right here. And then the next one will be most of those properties have a size around 884 square feet. Basically, there's a lot of graph here, and then this is lots more of graphs. Okay, you can look through it when you take a look in our videos or take a look at our code here. This is a bar plot, so it's some patterns here. Basically, most of the properties we can see that they have 3 rooms and then 2 bathrooms. Usually comes with 0 to 2 parkings for all the properties here. Then the next one is correlation. You can look through it, pre-processing for linear regression. And through it also because it's linked to the next linear regression here. Yep. So we'll get into the next one. So this is the linear regression that we are going to talk about right here. So basically, if the linear regression is with the PCA model, PCA method, so basically everything that you see right here is this the actual versus predicted values. This is the residuals versus predicted values, and then this is the predicted. This is the predicted is the x, and then the y is the residuals lah. As usual, that is the distribution of residuals and the count. So you can see this is the highest point you can see here. So for this model, the coefficient shows that for every 1 unit increase in PCA1, the monthly rent is expected to decrease by approximately 176.20, all else being equal. And then this is the most important part, and then most of the values here you can look through it. Is the monthly rent in PCA2 is expected to decrease by approximately 88.78, and most of the root mean square error is 395, and it actually shows the difference between the predicted and actual monthly rent. In the model, in R model 2 of approximately 0.363, which means around 36.3% of the variance in our dependent variable can be explained by our independent variables. And then for the next one, the next code here will be the linear regression without using PCA. So it actually is we're doing the same thing, which is the actual versus predicted values graph, residuals versus predicted values graph, and then also the distribution of residuals graph. So in this model without PCA actually has lower MSE, Lower MSE means that in the second model has a better fit compared to the first model, as it has lower average square errors between the predicted values and actual values. Our RMSE is 351.848, lower than the first set of results, which is the RMSE comparison. Means that the second model has a better fit as it makes smaller errors in prediction. So in second model, also in the R square of 0.4965, it has higher, means that we have 49.65% of the variance in the dependent variable. The result in this not using PCA is better than using PCA. Might be causes by loss of information. So, but what means by the PCA is that PCA reduces the dimensionality by combining existing features into a smaller set of principal components, while the components are designed to capture the maximum variance possible. So they might not remain their information needed to predict the target accurately. And that's all from me. So maybe after that you can take a look if the clustering analysis below, which presented by another person. So basically that's all from me. Alright, thank you.
So I'm usually and I'm doing for the clustering analysis part for our project. So these are the features chosen for clustering analysis. So before clustering, we will apply standard scalar as the standardization for our data. Then we will apply the PCA to convert it into two PCA components. So after that, we use the WCSS to calculate the optimal number of clusters. So we can see using the elbow method, the optimal cluster is 3. So we will feed it into the k-mean clustering, feed the data into the k-mean clustering. So we can see the cluster point are well separated using PCA1 and PCA2. So for next part, we visualize out the distribution of the numerical data for each cluster. So in this case, monthly rent and size for cluster 1, cluster 2, and cluster 0. And for next part, we also visualize the categorical data for each cluster using bar plot to see their distribution. So these are the summarize of the characteristic of every cluster. So we have cluster 0, cluster 1, and cluster 2 characteristic. And this part is the finding. So for model evaluation, we will be comparing k-mean clustering and hierarchical clustering using PCA and without PCA. So we can see that the COS score of the highest COS score for the model is 0.42, which is the k-mean clustering using PCA, which is the model we use for both. And these are the additional findings. Thank you.